all. The first thing is that if X is an inner product space, the first thing that defined was that C is a complete orthonormal set if whenever somebody is orthogonal to everybody in C, then that means X must be the 0 vector. That is one of the definitions we gave, and the other one we said was C is called, whatever notation you want, C or whatever name, C is called an, of course it is an orthonormal set, okay, is called a maximal orthonormal set. So, let us say C an orthonormal set. It is called complete if this happens, it is called maximal if it is not a proper subset of any orthonormal set. You can't expand it and then still have an orthonormal set. So, these two notions we had, the notion of complete orthonormal set and maximal orthonormal set. And then we proved the following statements are equal. Statements are equivalent. Any one of them is true, all of them are true. This is the main result we had before. So, the first thing is C is complete orthonormal set. The second statement is C is maximal orthonormal set. The third is the Parseval's identity, norm x squared is equal to the x phi squared, where phi runs over the support. Remember that there will be only a finite countable number of them for which it will be non-zero, and that is called the support of x, okay, where Sx is the set of all phi in C such that x phi not equal to 0. And we have seen that this will be countably infinite for every x in X, for every x in X. The fourth is the Fourier series, x is equal to summation phi belonging to Sx, x phi phi for every x in X. And the fifth is the inner product is equal to summation phi belonging to Sx intersection Sy x phi y phi bar. All these statements are equivalent. If one of them is true, everybody else is true, and if one of them is false, all others are false. Okay. So, all this is what we had. Okay. This is the notion of a basis that we want to work with in Hilbert in inner product spaces. So, we raise the question, so it is enough if we have one of these, then automatically others follow. How do we know there is a maximal orthonormal set in this is the question is similar to vector spaces. We said a basis is a maximal linearly independent set. Then we ask how do we know every vector space is a basis. Then we use Zorn's lemma and prove it exactly the same way we prove it. Okay. The proof follows using Zorn's lemma. Let me quickly indicate what it is about. So, what we do is, first of all, we are looking for a maximal orthonormal set. We are not even sure whether there will be an orthonormal set to start with, leave alone maximal. So, let us make sure there is some orthonormal set. So, first of all, obviously we are taking a space which is non-trivial, it has non-zero vectors in it. If the space has only 0 vector, there is nothing in that space to study. Okay. So, first there exists an x not equal to theta x, x belonging to x. In that case, you can take a unit vector in that direction, that single vector forms an orthonormal set. Okay. So, then let phi equal to x by norm x, then the singleton set phi is an orthonormal set in x. So, at least we do have orthonormal sets. So, therefore, there exists orthonormal sets in x. That is the first thing. Then we take all the possible orthonormal sets. Okay. So, let O be the collection of all orthonormal sets in that space. Obviously, this is a non-trivial collection, because we already seen that there are orthonormal sets. There is at least one, because there will be one non-zero vector. Okay. Clearly, by 1, O is a non-empty collection. Whenever there is a non-empty collection of sets, you have a standard partial order, namely the subset are equal to. Okay. Then is a partially ordered set. So, what we are trying to say is we want to find a maximal element in this partially ordered set, and the existence of a maximal element in partially ordered set always comes from Zorn's lemma. That is a standard technique to show the existence of a partially ordered set. Okay. So, what we are looking for is a maximal element of this poset, partially ordered set. So, the existence of such a poset, the existence of a maximal element is guaranteed in a poset, is guaranteed if the conditions of Zorn's lemma are satisfied. The Zorn's lemma says under certain conditions there will be a maximal element, guaranteed. Under certain conditions there is going to be a maximal element. What are these conditions? Okay, that is the condition says if every chain in this poset has an upper bound. So, this condition has to be satisfied. If every chain in this poset has an upper bound, we are guaranteed a maximal element. So, we have to go through these words. What is meant by a chain? What is meant by an upper bound? Okay. So, a chain means a collection of elements in that poset is called a chain if every pair of elements in that is comparable. That is, give me two elements in it, either A is below B or B is below A. Okay. So, chain means, this word chain means every pair of elements is comparable. Upper bound means something that nobody can cross, that is, everybody is smaller than that. That is, an upper bound U if X is S is contained in U for every S in the chain, then it is called an upper bound. Everybody is smaller than him. So, we must first show that every chain has an upper bound. Okay. If we show this, you take any chain in this partial orderless set and then show that it has an upper bound, then Zahn-Schlammer says, since every chain has an upper bound, it must have a maximal element. So, we need to show this. So, we now show that star is satisfied. What do we have to do to show that? Every chain. So, start with any chain. Okay. So, let K be any chain. In this partial ordered set. Again, let us recollect what is meant by any chain. First of all, it is a subset of O. O itself is a collection of orthonormal sets. So, every element of K is an orthonormal set. Every element of K is an orthonormal set in the inner product space. Okay. So, that is K is contained in O. This means K is a collection of orthonormal sets in X. O is a collection of all orthonormal sets. So, K is a subcollection of orthonormal sets. That is K being in this. This is the in part. Chain means what? Chain means if S1 and S2 are elements of K. What are elements of K? Elements of K are themselves orthonormal sets. So, S1 is an orthonormal set, S2 is an orthonormal set, then either S1 is contained in S2 or S2 is contained in S. That is what is meant by saying every pair is comparable. Either this fellow is smaller than him or that fellow is smaller than this fellow. One of these two must happen. Okay. We know that in a general partially ordered set, we may have two elements which are not comparable. Okay. But in a chain, every pair must be comparable. So, this is what we have. This is given to us. We want to show that there exists a U in this partially ordered set. What does that mean? U is another orthonormal set, okay, such that is an orthonormal set U such that it must be an upper bound such that S is smaller than U for every S in K. No orthonormal set in K can be bigger than U. This is what we have to show that you start with a chain, it must have an upper bound. So, you have started with a chain, we want to show that this is an upper bound. Now, we are going to construct that upper bound. So, this is now our problem. Now, we want to show double star. To show star, now it is, so now we show double star. Now, let us look at what should be the requirement of U. Every set in K must be contained in U. Therefore, if I put them all together, they will all also be in U. So, U must contain all the things that are in K. So, what we do is we put them all together. So, let U be equal to the union of all the orthonormal sets belonging to K. Any element of K is an orthonormal set. So, take all the orthonormal sets belonging to K and take their union. Clearly then this is true, because U is the union of everybody. So, certainly everybody is part of it. Therefore, clearly therefore, S is contained in U for every S in K. So, this part is already over. The only thing now that remains to be shown is that U is an orthonormal set. If we show that U is an orthonormal set, then he is an element of the poset and he dominates everybody in the chain, and therefore, he becomes an upper bound for the chain. So, it remains to show that U is an orthonormal set in X. That is all that is to be shown. If we show this, then I have an orthonormal set which dominates every member in that chain K. Therefore, the chain K is an upper bound. John's lemma guarantees the maximal element. So, that is triple star. So, finally, it boils down to this. So, what does it mean to say that it is an orthonormal set? I must take two elements and show that their dot product is 0 if they are different, and the dot product is 1 if they are the same. So, first of all, we will show that the length of any vector is 1. Okay. So, now we show 3 star. Slowly we boil down, come to the trivial stage. Okay. We now show 3 star. One, X belongs to U implies what? U is the union of all these fellows. Therefore, he must belong to one of them. Because it is in the union, it implies there exists an S in K such that X belongs to S. Because U is the union, he must be in one of the members of that union. But now, K is an orthonormal set, because K is a chain. K is a chain in O, and therefore, K consists of only orthonormal sets, and therefore, S is an orthonormal set, implies norm X equal to 1 since S is an orthonormal set. So, which implies X comma X is equal to 1. So, that part is over. Every vector is normalized to length 1. The only part that is left is to show it is ortho. Any two vectors are orthogonal. So, the orthonormal part, in the orthonormal part, we have shown the normal part. We have to only show the ortho part. That is next, X and Y, XY belongs to U, X not equal to Y. Suppose I take two different vectors in U, I must show that they are orthogonal. Now, U is the union. Therefore, there must be some element of K to which X belongs and some element of K to which Y belongs. Okay. So, This implies there exists an Sx in K, Sy in K such that x belongs to Sx, y belongs to Sy, because it is in the union. Each fellow should belong to one part of that union. Now, Sx and Sy are in K. K is a chain. Now comes the chain. And therefore, either Sx is contained in Sy or Sy is contained in Sx. And therefore, if Sx is contained in Sy, both xy are here in Sy. If Sy is contained in Sx, both are in Sx. Okay. Implies xy belong to same orthonormal set because either Sx is contained in y or Sy is contained in Sx since K chain. Then we are done, because it belongs to an orthonormal set, x comma y must be equal to 0. Because they belong to an orthonormal set and they are different vectors, the two must be orthogonal to each other. So, that is the complete proof. Slowly we brought to that stage. So, what we did was, first we showed that there are orthonormal sets, then we showed take all the orthonormal sets, make it a partially ordered set. In that partially ordered set is where we are looking for a maximal element, and to look for maximal element, look for Zorn's lemma. To apply Zorn's lemma, you need to show that every chain has an upper bound. So, we took an arbitrary chain, we really constructed the upper bound and we verified that that is indeed the upper bound. So, now we are assured that every inner product space does have a maximal orthonormal set and hence a complete orthonormal set, and hence Fourier series can be done, partials identity can be done, everything can be done. So, this is a typical proof of the existence of most of the time basis. This is orthonormal basis. In the case of vector spaces, we had Hamel basis and so on and so forth. Okay. So, now we are assured of an complete orthonormal basis for any inner. Just like we are assured any vector space as a basis, we are now assured that every inner product space has an orthonormal basis. Now, let us take the simple situation first. Okay, let me make a comment. Just like a vector space may have many bases, an inner product space may have many orthonormal bases, many maximal orthonormal sets. But just as in the case of vector space, any two bases have the same size, any two complete orthonormal sets will have a same size. I will not prove it, but it can be shown that in an inner product space, any two maximal orthonormal sets have the same cardinality. So, this cardinality is another dimension, it is called the orthogonal dimension or the Hilbert dimension of that space. Okay, that cardinality is some kind of a number associated with that space. But it does not exclude the possibility that the maximal orthonormal set could be uncountably infinite. That possibility is still there. All we say is if it has one uncountable orthonormal set maximal, then all maximal orthonormal sets must be uncountable and all of them must be the same cardinality. If one has the cardinality of the real numbers, and all of them should have the cardinality of the real numbers. Okay, so let us take the simple case now. Consider the simple case where has a complete orthonormal sequence phi 1, phi 2, phi 3, etc. That is, the basis is now a sequence, infinite sequence. Of course, finite we have already studied, that is linear algebra, finite dimensional linear algebra. Okay. So, next step is to have an infinite sequence of orthonormal vectors which form a basis. Okay. Remember those 6 statements we made, 4 or 5 statements we made. Once you have a complete orthonormal basis, it is equivalent to saying anybody is orthogonal to him, all these fellows must be 0 vector, and this cannot be expanded into a bigger orthonormal set. Everybody has a Fourier series in terms of this. Everybody satisfies the Parseval identity with respect to this. Everybody satisfies the Plancherel's formula with respect to this. So, in particular, we have, therefore, we can expand every vector x in X as a Fourier series with respect to this orthonormal basis as x equal to summation n equal to 1 to infinity x phi n. Okay. This because once you have basis, automatically we said Fourier series will follow. Now, given the vector x, these are numbers calculated with from the vector x through this basis. So, let us call this, we call, let x n be equal to x phi n. Okay. Now, these are all numbers. Now, consider the vector. X, what shall I call it? Capital X, shall I call it? Okay. To be x1, x2, etc. The usual vector with infinite components. Okay. What does that mean? You start, if you are given an orthonormal basis, which is a sequence. So, if you have an orthonormal sequence as a basis, starting from every vector, you can construct a sequence of numbers. Okay. So, therefore, and what else? Note, by Parseval's identity, we have norm of x squared is summation n equal to 1 to infinity mod x n squared, that is Parseval's identity. And therefore, this is a vector in the norm in the inner product space. Every vector has a finite length, therefore, this is a finite quantity. Therefore, summation n equal to 1 to infinity mod x n squared is less than infinity. What this says is, this sequence that we have constructed, this is precisely the statement that this sequence belongs to L2, little l. So, therefore, x belongs to L2. Let us assume everything is complex. If it is complex, it is L2 of complex. If it is real, it is L2 of real. Okay. So, real inner product space, I will write L2 of R. If it is complex, this thing I will write, just I leave it as L2. Therefore, what we have done is, on the one hand, we have this inner product space. On the other hand, we have our very familiar standard inner product space L2. Okay. Now, with every vector x here, we have associated a vector capital X there. So, let us call this transformation as phi, because this identification has come through this basis phi 1, phi 2, phi n. So, let phi be a mapping from x to L2 defined as phi of x is equal to x. Oh, I have this is a terrible notation, right? There are too many x's. So, what shall I call this? I will call it as some x hat then this is little x hat, because the space also I called it as x hat, capital X. So, this is x hat. Okay. This is like a Fourier transform. Actually, it is a Fourier transform. Okay. If you take the Fourier series, this is a discrete continuous time discrete Fourier transform. This is the counterpart of that. Okay. Right. So, what we have done here is with every vector x in the inner product space, we have associated a vector in x hat. Now, clearly phi is linear, because if you add two vectors, corresponding components here get added. If x is x phi n phi n, y is y phi n phi n, x plus y has the x phi n plus y phi n as the coordinate. So, that is very trivial. So, phi is linear, phi is norm preserving, because what is norm of phi x? Phi x is x hat, it is equal to norm of x hat. The norm of x hat is mod x n square. X hat is this vector, so the norm of x hat is this x n squared, but x n squared by Parseval's identity is norm x squared. This is Parseval. So, therefore, norm of phi x squared is equal to norm of x squared. Therefore, norm of phi x is equal to norm of x. So, therefore, it is norm preserving. The moment it is norm preserving, it is automatically continuous. If x n goes to x, the norm of x n minus x goes to 0, but norm of x n minus x is the same as norm of phi x n minus phi x. Therefore, phi x n goes to phi x. So, phi is continuous. Okay. So, therefore, phi is continuous, also continuous. So, it is a continuous linear transformation. So, what are we doing? We are now in a sense we are coding every vector in an inner product space as an L2 vector, or we are digitizing every vector in an arbitrary inner product space. An arbitrary inner product space, once you choose an orthonormal basis, every vector can be digitized through that, and you come to L2, which is our number space. Okay. That is the great digitization that you can achieve for any arbitrary inner product space. Number 3, this digitization is 1 1. There is no confusion about the code. If x is not equal to y, x hat will not be equal to y hat, or x hat equal to y hat if and only if x equal to y. So, phi x equal to phi y implies that x n equal to y n for every n, which implies x n minus y n equal to 0 for every n, which means the vector x minus y is orthogonal to phi n for every n, because that is exactly what x n minus y n is. But if a vector is orthogonal to all the vectors in the basis, that vector must be 0. That implies x e minus y equal to 0, because phi n is orthonormal basis. That implies x equal to y. So, phi x equal to phi y implies x equal to y, and therefore, phi is 1 1. Right. So, there is a beautiful coding that takes place. of all the vectors in an arbitrary inner product space through a orthonormal basis can be converted to the number space L2, which preserves norm, which is very distinct fellows are identified with distinct vectors. It preserves norm, which maintains approximations because it is continuous. So, therefore, limits are preserved. The only problem will be, is everything here a code of that, something there. In other words, is capital phi onto. Okay. If capital phi has to be onto, since this is complete, naturally this must also be complete because it is non-preserving. If that fellow is complete, this fellow is also complete. So, therefore, that question does not make sense unless this fellow is complete. And therefore, if you have a Hilbert space, if this place is complete inner product space, if it is a Hilbert space, then you may ask, is it going to be onto? So, let us look at that question. Is phi onto? That is, given x hat in L2, can we construct x in capital X such that capital phi x is equal to x hat? That is what is meant by onto. Everybody there is the image of somebody under phi. Is this map onto? And very obvious. Well, choose them as the Fourier coefficients. Okay. So, given x hat in L2, so it is x1, x2, etc. Consider xn to be the vector k equal to 1 to n xn phi n. Okay. Now, what is xn minus xm norm squared? Obviously, if you write xn minus xm comma xn minus xm, all the cross terms will be 0 because phi n's are orthonormal. So, you are going to get, let me write that, summation n plus 1 to m xn k xk, and this should be xk phi k, xk phi k, summation n k equal to n plus 1 to m xk phi k. Okay, that inner product. When you take this inner product, what happens? Because the n fellow will stop at n, m fellow will go up to m. If you subtract, all you get is from n plus 1 to m. Now, if we take this inner product, cross terms will go. What will I get? The diagonal term phi k will be 1. I will get xk bar, which is mod xk squared. Now, remember, this is in L2. If this is in L2, summation mod xk squared is finite. If this is finite, what can we say about the tail of that series? That will go to 0 as n and m go to 0. This tends to 0 as n and m go to infinity, because x hat belongs to L2, and therefore, summation mod xk squared 1 to infinity is a convergent sequence, convergent series. Therefore, the partial sums form a Cauchy sequence. So, what does that say? xn is a Cauchy sequence in capital X. Therefore, xn is a Cauchy sequence in capital X. Now comes the Hilbert space hypothesis. If this space X is complete, every Cauchy sequence will converge, and therefore, xn will converge to some x. So, if capital X, if capital X is complete, that is, it is a Hilbert space, that is, if X is a Hilbert space, then every Cauchy sequence converges therefore, x n converges to some x in x, which means this series converges, that is x is equal to summation n equal to 1 to infinity x n phi. For this vector, what is x phi n? Precisely x n, okay, and therefore phi x is x hat, and we are done. Therefore, phi is what? The image of this constructed vector is precisely that x hat is started with. Therefore, phi is on. Okay. So, what is the moral of the story? This identification is fantastic. Every vector in a very abstract Hilbert space, as long as it has a countable orthonormal basis, can be completely identified with L2, vector to vector, 1 1 onto complete translation both ways, and continuous non preserving, automatically inner product preserving also. Okay. Clearly, the other one is easy to verify, that is, and fifth one is the last thing to observe is that phi x comma phi y is equal to x comma y. So, the geometry is preserved, topology is preserved because norm is preserved, geometry is preserved because inner product is preserved, identification is completely preserved, 1 to 1 on 2. So, forget about that space, you could as well study this space. So, what does that say? Actually, there is only one Hilbert space with a complete orthonormal sequence. All other Hilbert spaces are the same Hilbert space written in a different language. Okay. So, there is only one concrete model of a Hilbert space with a complete orthonormal sequence. If you know little L2, you know all Hilbert spaces with complete with a complete orthonormal sequence. That is all. There is nothing else. There is only one. So, this is the model. This is the concrete model of all Hilbert spaces which have complete orthonormal sequence. Okay. So, any Hilbert space you take, it is digitized, it is brought to this, it can be brought to this level. So, there is really no problem with dealing with Hilbert spaces with complete orthonormal sequence. Remember, we also identified this as the capital L2 over an integer set with the counting measure, capital L2 with the counting measure. So, basically you can therefore say the capital L2 on a countably infinite set with counting measure takes care of all Hilbert spaces which have countably infinite orthonormal sets. Okay. So, now I am going to make more statements about this Hilbert spaces with countably infinite orthonormal. So, let us put this as a theorem. Okay. Hence, we get the theorem any inner product space, any Hilbert space which has a complete orthonormal sequence. that is its Hilbert dimension is all F naught. Its Hilbert dimension is the dimension of the integers, is completely identified with little L2, that is L2 of n. That is the essential theorem. This is like there is but one God, there is only one Hilbert space, all others are different avatars of that same God. Okay? There is nothing more than that. Okay. So, after studying L2 and after doing all these inner product Hilbert spaces, that do not worry, these are all only same different religions, they are the same things, they say the same truth, okay? All say the same Hilbert space. Right. Now, let us look at such a Hilbert space. Okay. We already know that little L2 is separable. It has a countable dense subset, namely take all vectors with a only finite number of coordinates which are rational numbers, and that forms a countable dense set. Since L2 is separable, this space must be separable. Since L2, what is the spelling of separable? Separable, it follows any such Hilbert space is separable. So, this theorem can be stated as every separable Hilbert space is isomorphic. This is what it means, isometrically isomorphic, is identified vector to vector, the transformation is 1 1 on 2. So, algebraically identified, topologically identified, metric wise identified, inner product wise identified. So, I will simply write the completely identified with little L2. So, now what about the non-separable Hilbert spaces? Separable Hilbert spaces, that study boils down to little L2. So, I will come to separable non-separable Hilbert spaces little later, but now let me make one or two simple comments about separable Hilbert spaces. So, a separable Hilbert space is something which has a complete orthonormal sequence. Okay. Now, because there is a slight technical point I did, but both ways I have to show, but it is trivial. Anyway, let us now look at a Hilbert space generally. Let us not even bother about separability. Suppose I do not even worry about for the moment Hilbert space. Let me look at an inner product space. So, let us look at an inner product space. Just like linear algebra where we did, any linearly independent sequence of vectors can be converted to an orthonormal sequence by the Gram-Schmidt. Okay. So, Gram-Schmidt. If U1, U2 etc. is a linearly independent set in X, we can construct an orthonormal sequence phi 1, phi 2 etc. such that the space spanned by U1, U2, Un is the same as the space spanned by phi 1, phi 2, phi n for every n. At every stage we sweep the same spaces, and the process is called Gram-Schmidt process. The same story. How do you do that? First, you take the U1 vector, divide V1 to be U1, then phi 1 to be V1 by norm V1. Okay. that is a unit vector. Then V2 is from U2 you remove the information along the phi 1 direction. What is the information along the phi 1 direction? U2 comma phi 1 comma phi 1. Then take phi 2 to be the normalized vector. So, proceeding thus, so having got phi 1, phi 2, phi n minus 1, recursively get phi n as, first you get V n, which is from U n, you subtract all previous informations j equal to 1 to n U n phi j, and then define phi n to be V n by norm V. So, if you get 1, you get the second. If you get the first and the second, you get the third. If you get first, second, third, you get the fourth. So, now by induction, you get all of them. This is called the Gram-Schmidt process. Now, historically, if you see in differential equations, while the theory of differential equations, people studied what are known as Sturm-Liouville problems, they came up with very many orthogonal polynomials, Legendre, Laguerre, Hermite, Jacobi. There are an infinite number of polynomials, orthogonal polynomials. All of them fall under this category. That's all. Okay. So, what you do is you take the space of all continuous functions over an interval I. Okay, let me call this space as X. All continuous functions over an interval I. Define, I will put here a suitable inner product on C, on X. I will say what we will see what is meant by suitable inner product. So, define a suitable inner product on X. Then consider the linearly independent set U1 equal to 1, U2 equal to x, U3 equal to x squared, Un equal to x to the power of n minus 1 and so on. The 1 x, x squared, x cube, they are all linearly independent. So, take this linearly independent set, you have now an inner product, apply Gram-Schmidt. You are going to get a orthonormal sequence. At first stage you will get constant, second stage x minus something, so first degree polynomial, second stage you will get second degree polynomial, third stage you will get third degree polynomial. So, you get a sequence of orthonormal polynomials, phi 1 x, phi 2 x, etc. This gives us the so called orthogonal, the whole subject of orthogonal polynomials. Okay. These are books and books written on orthogonal polynomials, but all of them are captured in these 4 lines. Start with the space of all continuous functions over a suitable interval, define a suitable inner product, apply Gram-Schmidt, you get it. Let me explain what this means. For example, example 1. Let us take I to be the interval minus 1, 1 standard. In that case, I can simply define the dot product of f and g, the inner product, to be defined as integral fx gx bar dx minus 1 to 1. See, if we take f and g continuous functions, the product is continuous, so it is nicely integral. So, no problem, it is a finite interval, everything is well defined. So, that is the difference. So, now apply Gs. So, apply Gs with this setup. With this setup, what you get is known as the Legendre polynomials or the orthonormal Legendre polynomials. He looked at it from the point of view of differential equations and used the Sturm-Liouville theory and got this polynomials. Okay. But that is exactly what is happening. Now, suppose my interval is 0 infinity. In that case, this inner product will be terrible, because suppose I take the function f of x to be x and g of x to be x squared, I will get x cubed dx, and I integrate between 0 and infinity, I will get infinite value. So, that is not a good thing. So, therefore, where is the problem? The problem is when I go to plus infinity. So, kill it by putting a e to the minus x. Okay. So, define the inner product as integral 0 to infinity f x g x bar e to the minus x dx. Now, everything will be taken care of, okay, because that e to the minus x goes first very fast to 0, it will take care of x or x squared, x cubed, x to the power of 4 or any polynomial it will take care of. And now you do GS. What you get is the so called Legendre polynomials. Okay, the orthonormal Legendre polynomials. Okay, so the example 3. Take I to be minus infinity infinity. I am giving 3 examples. One is a finite interval, the other one is a semi-finite interval, a semi-infinite interval, the next one is fully infinite interval. Now, where is the problem going to be? Both at minus infinity and plus infinity. So, e to the minus x won't work, minus x squared will work. Okay, so that is all. So, define f comma g to be integral minus infinity to infinity f x g x bar e to the minus x squared dx, and then apply GS. What you get is the orthonormal Hermite polynomials. Pardon me? Legendre polynomials. Okay. They are denoted by Lx, but unfortunately they are divided by Lx. But what about Legendre? Okay, somehow they are originally polynomials. Okay, that was the first one. They were denoted by Pnx. These are denoted by Lnx. These are denoted by Hnx. Hermite, not Hilbert. Okay, so it's a little difficult to. So now, what all this boils down to is, suppose you are looking at arbitrarily any interval, you look at a proper probability density function which has all moments finite, so that I can put x to the power of n dfx or px dx. So, suppose I have a probability density function fx such that x to the n fx dx is finite, then I can apply GS and I will get the orthogonal polynomial. So, start with any probability density function on any interval which has all moments finite and apply now the Gram-Schmidt, you will get a set of orthonormal polynomials. So, there is, I can have a polynomial in my name, I can have many orthonormal polynomials in my name by tweaking this and this. So, there is no end, okay, to this. Initially, this came from differential equations, the so called Legendre's differential equation, Hermite's differential equation, Legendre's differential equation. But afterwards, people found out the trick of the trade. They said all that is not necessary, you just simply do this, you can get any number of orthonormal polynomials. So, corresponding to every probability density function which has finite moments, all ordered moments are finite, we can generate a orthonormal set of polynomials. Now, one comment with which I will compute. Now, what about the Hilbert situation? This sequence forms an orthonormal basis in L2 of minus 1 1. All functions which are square integrable on minus 1 1. This sequence forms an orthonormal basis in L2 of functions in 0 infinity with this inner product, with that inner product. Okay. So, because otherwise that integral may not be finite. In other words, this is the set of all functions, that is the set of all functions from 0 infinity to c such that integral mod f squared e to the minus x dx 0 to infinity is finite. So, that density function e to the minus x must come in the definition. And similarly, this forms an orthonormal basis in L2 of minus infinity infinity with this inner product, that is the set of all functions mapping minus infinity to infinity to c such that minus infinity to infinity mod f squared e to the minus x squared dx is finite. Okay. That is that space, it forms a orthonormal base. These are all Hilbert spaces for which this is basis, and so these are all the corresponding. All these are again identified back to L2 through this process we went through. Okay. So, these look like very complicated spaces, but finally they are identified with little L2 and all of them get digitized. Okay. Right. What was I? Where was I? Well, incidentally, the physicists put e to the minus x squared and the probability theorists put e to the minus x squared by 2 to identify it with the 2 sigma squared with variance 1 and mean 0. Okay. So, they put an e to the minus x squared by 2 is the probabilist notation, that there is another set of polynomials, there is a little different normalization, same Hermite, and the physicists originally started with e to the minus x squared. So, this is the physicists, and e to the minus x squared by 2 is what the probability theorists use. Okay. That variance 1 and mean 0 situation, 2 sigma squared is 1. Okay. So, therefore, all these orthogonal polynomials are nothing but simply Gram-Schmidt process done with a suitable inner product. That is all, very simple as that. So, the model that we have today is, if we have a separable Hilbert space, no problem, it is only little L2 different language, and little L2 is capital L2 of n with the counting measure. Next, we will see that non-separable spaces are also identified now with capital L2 counting measure, but not that set n, but an uncountable set. That is all there is. So, basically all Hilbert spaces are L2 spaces. That is the final theorem. All Hilbert spaces will be L2 spaces, and therefore, it is enough to study L2 spaces. That is why all this finite energy thing is important, because every Hilbert space is some kind of a finite energy thing. Okay, I think I will stop here. We will meet tomorrow, same 5 o'clock.